Ah, look at all the lonely people. Okay, so what we're doing now is we're looking at non-uniform motion, or what we can also call it as a constant uniform acceleration, because our object will be moving and then it could be accelerating at some point. So generally speaking, and these are our notes here in the Unit 3 section, what we always want to do is, like old Grandpappy Bosser taught us, we want to sketch a diagram of the situation. We then want to identify what's going on with the motion, and then with what information is given, we need to decide which equation using our best friend forever. It's our best friend. Which of these equations going to be going on? Is it 1 if we have 0 acceleration, or is it equations 3, 4, 5, 6 if the acceleration is not 0? And remember, equation 2 is just equation 3. Okay, so let's take a look at this example and figure out what should be going on. So we've got a mouse car, and if you're unfamiliar with a mouse car, these are old-timey toys with, like, you put the key in the back, and then you wind it up, and then you set it down, and it moves along the ground. Okay, and the cool thing about these is they kind of move uniformly, and then zoom, they zip up, and they speed, and they accelerate sometime later. So what's going on here is we've got a little picture, okay, and if you want to draw one, you can draw one as simply as this. Here goes a poor drawing. It's a car. Here's the little key in the back. And it goes 10.3 meters. So this is 10.3 meters. So this is a delta x. And it does this in a time of 4.15 seconds. Okay? And it's moving at a constant velocity. Now, if it's moving at a constant velocity here, this means that we have a constant velocity. That's equation 1. Okay? So this is equation number 1 over here. It then, so this is the second part, it then accelerates at a value of 1.22 meters per second squared for a time period of 5.34 seconds. We'd like to know what total distance did it travel. So going from the start back here to the end out here somewhere, what is this total delta x? Okay? So, oh boy, this is going to be tough. So let's, for this problem, start at the beginning and then work our way on, because we know that over here for the second part, since we have an acceleration, we're going to be using equations 3, 4, 5, and 6, and if we want to use those equations, we need 3 out of the 5 possible things that could exist over there, and at the moment, we only have 2 of them. Wah, wah. So let's do this. Let's start at the beginning and see if we can use something here to take us further, okay? So for this mouse car, it's traveling at a constant velocity here. So it has this same velocity at the beginning and at the end here. So let's try to figure out what that velocity is. Well, if we go ahead and use equation 1, we know that the velocity is just equal to a displacement divided by some amount of time. So that's just going to be 10.3 meters divided by the 4.15 seconds. That'll give us meters per second. So what is 10.3 divided by 4.15? 10.3 divided by 4.15 is 2.48. Let's just round that up to 2.5. I'm not super concerned about sig figs or whatnot. Let's talk about the physics here, okay? So we've got 2.5 meters per second. Well, this 2.5 meters per second, that's how fast it's going at the start, and that's how fast it's going at the end. But this end here, which I'm shading in green, this is also the start, the initial point of the second section in red, which means that this initial velocity right here, we could say that initially this velocity was 2.5 meters per second, because right here, when the car gets to here, it has this velocity, the 2.5 we just found. So now we actually have an initial velocity, we have an acceleration, we have a time. That's 3 out of the 5 possible things. That means we can go solve for some other things there. And what would be nice to find is if we could find this second displacement here, if we could find this delta x, we could just add it to whatever we had in the beginning and get the total thing. So this is very much just an equation picker again. We have a VI, we have an A, we have a T, we're looking for a delta X. So we have a VI, we have an A, so there's the VI, here's an A, here's an A, here's an A. We have a T, we have a T, we have a T, We have a t and a t. And we're looking for delta x. So we're looking for this delta x here. So we take a look at these. It can't be 3. It can't be 4. It can't be 6 because we don't have this VF. So we're left with equation number 5. And what's nice about equation 5 in this case is because we're not looking for time, we don't actually need a quadratic. We can just shove in numbers here. So to shove in numbers, we just plug them in. We can say that the delta x for equation number 5 is going to equal the initial velocity, 2.5, multiplied by a time, 5.34, plus 1/2 times the acceleration of 1.22 times the time, 5.34, and don't forget to square that, okay? So it looks a little long, but they're all numbers, and if we just grab a calculator that we've had since we were in high school 600,000 years ago, we can solve this. So 5.34 squared is gonna give me 28.5. And I'm going to multiply that by 1.22 to get 34.7. Then I'm going to divide it by 2 because of the 1/2. So I'm going to get a plus 17.4. And that's going to be meters. And I like to kind of keep track of my numbers as I go along in case I make a mistake. It's a good habit to get into. And then let's multiply these together. 2.5 times 5.34. That's going to give me 13.35. So now if I want the delta x for the second part, I simply add them together. So 13.35 plus 17.4, I'm going to get 30 let's just round up to 30.8 meters. And remember, that was only the distance for the second part here. We need to add that to the distance from the first part, which we are given. So we can simply add this to the 10.3, and we'd get a total value of 41.1 meters. And that's it. That's how we set up a problem like this, okay? Really, it was nothing more than one of our equation pickers, but the kind of trick to this one was that we had to first go ahead and try to figure out what this velocity was here, because it was only with this velocity, once we found it, that we could go ahead and have an initial velocity for the second part. Okay, then it's just a matter of going up, picking the right equation, and running through a problem. So nothing much to that one. Pretty straightforward for one of our new kind of non-uniform motion problems where we have a possible acceleration there. But this is finished. You can try out some of our practice problems we've got now sitting in the Google Drive section, and let me know how you do on those. Okay, but until next time, adios, take it easy.